Okay, in our prior video, we studied the foundation, the theoretical foundation of the GRACE mission, the type of data it collects, how that is converted to groundwater storage anomalies. And in this presentation, we're going to talk about the GRACE groundwater subsetting tool. This tool is a web application that's part of the apps.geoglows.org portal, and it's this one right here. And this tool can be used to process GRACE data for a region. So it takes the global GRACE data set, and it allows you to analyze groundwater storage anomaly and other parameters were aggregated or computed for a specific reason, hence the name subsetting tool. So this is what the tool looks like. When you launch it, you have the option of displaying it for the entire world. And this is currently showing the groundwater storage over here. And this raster that you see here is a time-varying raster. It starts in 2002, and it goes up to the current time, and it's a plot of the groundwater storage anomaly relative to the 2004 to 2009 period. And since it is a transient data set, you can use these controls down here to click play, and it will animate that map over time. And as the legend shows, this map is in units of liquid water equivalent in centimeters. So the blue means an increase in water relative to that baseline, and the reddish hues indicate a deficit of water relative to the baseline. You can also select regions that have been uploaded. You can pick them from a list, and then it will show you, it clips the global raster data set to only include the cells inside the region you're viewing. This is an aquifer in Niger in Western Africa that we studied as part of an earlier project. And then down at the bottom, you get a time series plot showing how the selected storage component varies over time. And then as you animate the plot above, there's a red bar that kind of cycles to show you where the particular raster image that you're seeing falls on this timeline as you play it. And it has a number of controls. You can use the layers menu here to change the symbology, and you can download these curves that you see here. You can click on this, these three little lines here, and then download that curve into an Excel file or a CSV file for visualization using some other tools. This is when you first launch the tool, this is what it looks like. You pick a region, and this region has to have been previously uploaded. If you're logged into the app as an administrator, then you have the option to add a new region or delete a region. And so someone has added, for this particular version of the app, added all these regions. And then you can pick that region and view it. So this is, if we select the Cuba region, this is what the map looks like. And initially when you load it, it defaults to the total water storage data set. You can also view groundwater storage, soil moisture, terrestrial water storage. And then again, down at the bottom, this is what the map, the time series of total water storage looks like. And it has a nice seasonal trend to it, which is clean. The groundwater data set is a little more messy. And then, again, the total water storage data set, as we learned in the previous presentation, is at a grid resolution of 0.5 by 0.5 degrees. If you switch to the groundwater storage data set, the groundwater storage anomaly, then it displays that. In this case, the grid cells are 1 by 1 degree. So these are the ones that overlap Cuba. And for this particular time step that's selected, you can see there's a deficit over here, and then some of these blue ones would be a surplus. This is the point on the line. It's a little bit messier. It's not as clean as a seasonal signal as we had with the total water storage. And we'll look more closely at that in some of our other plots. And as I mentioned before, if you're logged as an administrator, you can add a region. You upload a shapefile and then give it a name and click the button, and it loads it. It only takes a few seconds. It's not something that takes a long time to compute or subset. We do have extensive online documentation on the GGST tool at the URL shown here on Read the Docs, ggst.readthedocs.io. And you can, there's a language selector up here. You can switch that to Spanish or French or any other language you want, and it automatically converts that. And so now we'd like to look at some data specific to Cuba. We've uploaded the Cuba shapefile to the GGST app and done an analysis. And we exported that. This is the groundwater storage anomaly. It's been exported to a CSV file and then processed in some Python utilities that are included. Earlier I showed a slide of the online documentation. Well, that documentation has a link to a number of Google Colab notebooks that have very simple and easy to use Python to process the data you download and generate plots that are superior to the ones you get in the web app. And so this is the groundwater storage anomaly for the nation of Cuba, starting in 2002 and going up through first few months of 2004. This blue shading in the background is the uncertainty in the solution. So where that's narrow, there's a higher certainty. And there's some interesting things that happened back here. There was a pretty significant dip in the groundwater storage. It's happened a few times. Again, these plots are always going to be centered at about 0 in the 2004 to 2009 period. And so the differences are relative to that baseline. And as you can see, there's an overall increase in groundwater storage relative to that baseline in recent years. Another thing worth noting is there were gaps in the gray service. And the biggest gap is from about June 2017 to June 2018. The original gray satellites went offline in 2017 and came back online a year later. There were also some other, prior to that, some shorter gaps when the satellites weren't working. And this plot has those just connected with a straight line, but if you take those out, this is the same data, but without the straight line connecting the gaps in the data. And so you get the same general overall trend and understanding of the long-term trends, but it does give you an appreciation for the gaps. It turns out, however, that we have if you go to that documentation page, there's a Python notebook that uses a statistical technique that looks at patterns for periods when you do have data, and it uses a statistical decomposition method to fill in the gaps and give you an estimate of what the signature would have been during those periods. And in some cases, you know, it's a pretty safe bet. What that was, the gaps are relatively short. This is the longest gap, of course, but it's a very useful tool if you want to just have a more complete data set for visualization. Another thing that we like to do sometimes with the GRACE data is compare that time series of groundwater storage to precipitation trends in the region. Sometimes they're really highly correlated and sometimes they're less correlated. So NASA has a website called ClimateServe, and you just Google that, you can bring it right up. And if you click on this upload button over here, you can upload a GeoJSON or a shapefile, and then what it does, and then you pick a date range, and it has gridded precipitation data. I can't remember the exact resolution, but it's a pretty fine scale, and it finds all of the grid cells in this region, and then it aggregates those to get and you can download a monthly averaged, a monthly precipitation for the region. And then we have some, in the utilities portion of the documentation website, there's a notebook where you can read in the GRACE groundwater storage anomaly data set, which is shown here in red, and overlay that with the ClimateServe precipitation data to look at how they're correlated seasonally or more long-term. And this is plotting the actual monthly values, and this plot is kind of busy, so that notebook includes an option to compute multi-year moving averages. So this is a 3-year moving average, and then this is a 5-year moving average of the data. So this I think is a little more helpful in looking at the correlations, and you can see that as I mentioned earlier, there's a long-term increase in the groundwater storage especially over these latter years. And that, if you look at from about 2009 on, there's a pretty good correlation between precipitation and the groundwater storage. There is this anomaly in the precipitation signal back here, and I think it's associated with these. We have a spike here in precipitation and a spike here, and that caused an increase that for whatever reason wasn't fully captured in the groundwater storage change. But otherwise, that's a decent correlation and provides some interesting insight. Next, let's look at the nation of Haiti. I processed those data, and this is what the raw data look like. And in this case, there's an even stronger, a much larger increase in groundwater storage from about 2010 onward. With Cuba, it was up 3 to 5 centimeters, where now we're up around a 10 centimeter liquid water equivalent increase, which is pretty significant. In a lot of areas in the world, you see a pretty significant decline in groundwater storage. A lot of aquifers and basins around the world are being overutilized, where the groundwater is being pumped out faster than it's being replenished. But that's clearly not happening in Haiti. There's a surplus of groundwater that could be available for extraction. And once again, we have the gaps in the GRACE service. So this is what it looks like with the gaps displayed. I don't have the uncertainty bars on here now, but gives you a good idea of where those gaps are. And then this is what it looks like after those gaps have been imputed using our statistical tool. And again, if we process the ClimateServe precipitation, like we discussed earlier, and process that and overlay that and print it with the groundwater storage data, this one is really interesting. I don't see a strong correlation between precipitation and groundwater. in the nation of Haiti, which is rather unique. In most places that there's a pretty significant correlation, and for whatever reason, I don't see that. This is the 3-year moving average. This is the 5-year moving average. So again, it doesn't seem highly correlated. However, I still think this is a really useful plot, because if you look at the 5-year moving average of groundwater storage, you can very clearly see that it's almost a linear long-term increase. So we've just taken the noise out of this plot and smoothed it out, and we get this this really instructive plot of how the groundwater storage is changing over time.